Okay, we're returning to Chapter 10, Flow in Conduits, and we're going to do sections 10.3 and 10.4. Um, the learning objectives actually don't show section 10.4, but the main things that we're going to do in these sections are really determine the head loss, an equation for head loss in conduits. That means pipes and square conduits. And we're going to concentrate on deriving the Darcy-Weisbach equation. And we're going to be applying that equation later on in this chapter to determine head loss in pipes. And in addition, we will derive an equation in 10.4 for the shear stress. So this is what we're going to do in 10.4. So we're kind of concentrating on these sections right here, but really it's head loss and the Darcy-Weisbach formula, and then understanding how the shear stress can be calculated within a conduit. So let's go ahead and advance forward here to 10.3, right to this section here. And we're going to be concentrating on this Darcy-Weisbach derivation of this equation. And it's used to calculate head loss in a straight section of pipe. And before we start, we need to have an idea of what how we define the head loss. And we can see down here that the total head loss is broken out into two different components or two different terms. The head loss along the pipe, called the pipe head loss, and that's going to be added to what's called the component head loss, and which will be due to things like valves and bends and tees. Those are what we call components. And so the Darcy-Weisbach formula is going to describe this, the pipe head loss. Some alternative terms that are used for this are also major head loss for the pipe head loss and minor head loss for the component head loss. So let's remember that we're just dealing with this right now, and that later on in the chapter we will be returning to figure out how we deal with components, say when a pipe is making an angle, how we determine the head loss in those in tees and bends and valves and things that might be basically tying different pieces, components together, different pipes together. So let's take a look at the derivation here. So we need to use the momentum equation here to describe this situation. And we need to analyze what the forces are on this particular piece of fluid. And we note that there's a control volume here that's defined inside the pipe. And we're also going to assume that this is fully developed and steady. So we'll just write that over here. It's fully developed flow, developed, and it's steady flow. Okay, so we have fully developed and steady flow, and because it's fully developed, there's going to be net outflow or inflow into it. That's going to be zero, and there's not going to be any accumulation either because of the steady flow. So the equation is going to be reduced quite nicely, but we need to remember that the three forces that we have are going to be pressure, the pressure force. Of course, we have gravity when it's tilted, as is seen. This is the general case when the pipe is tilted. And we also have shear forces inside the pipe along the walls. So we'll just put shear here. These are the three forces that we need to write down. And because of these two things, and we don't have any net momentum flux or any accumulation of flux, the momentum equation is going to just reduce to the sum of the forces. So we can see the sum of the forces here are just going to be the pressure force, the shear force, and the weight of the fluid. And those are given in turn. This is the pressure force. It's just going to be the pressure difference. We go back here. and remember that we would be drawing a compressive force here, P1 on that end, and another compressive force, P2 on this end. Then those are in opposite signs of each other. And they also multiply, since that's force per unit area, they have to multiply by the area of the control volume. And this is just the shear stress times basically the volume. This is the area, the cross-sectional area, divided times the length of actually it's not the area, it's just pi times d times the length of the volume. If you take a look here, so this is the length here, delta L, and that's the shear force along the fluid, and this is the weight, which is just going to be gamma. Remember, this is mg over v over the volume, so we have to multiply it by the volume to make this mass times the acceleration of gravity. And we also have to take just the vertical component, so we have to have the sine of alpha. This can be reduced by noting a couple of different things here. First of all, we're going to kind of rearrange these gammas are going to get kind of rearranged in there. The pi's are going to cancel out since it equals 0 on the right. The pi's are going to cancel out, and in fact, the d squares are going to cancel out, except we're going to have an extra d over here. Yeah, and we will be, note that sine alpha also equals z2, this right here equals z2 minus z1 over delta L. So the delta L is going to cancel out, and we're going to get basically out of this, we'll get the gamma times z2. I'm sorry, gamma z1 z2. So that's going to give these two terms, and are going to come from here. The pressure terms are going to come from here, and we're going to move this stuff over to the other side. The other thing that we need to do is cancel the 4's. We get a 4 in the numerator here, which is going to be a little hard to draw, but we'll just stick it up here. So when we move everything over to the other side, we get this equation here with the shear stress over there on the right hand side. So we recognize this is the difference in the piezometric pressure here, and we note that that's going to equal this. Now we're going to rewrite this thing here in order to make it look more like the equation of head loss that we're used to. We don't see any v squares in there, so we're going to actually use the energy equation to deal with that. And if we remember now, the energy equation is P1 over gamma plus alpha 1 v. These are the average velocities. V, that's a v1. v1 squared over 2g plus z1 plus hp, the pump head. That's going to equal p2 over gamma plus alpha 2. This is, again, these are mean velocities. Plus z2, and there's going to be a turbine plus the head loss. Now this is what we want. This is what we're going to solve for, and we are going to note that this is 0 and this is 0, and that the velocities, because it's steady, are going to cancel out. And so if we rewrite this, as we've done quite a few times, we can write this now as the head loss is going to equal, I guess this is going to be gamma. Gamma times the head loss of P1 plus gamma Z1 minus P2 gamma. I'm sorry, P2, let me go back, see if I can erase those. Yep, P2 plus gamma Z2. Now, if we go back to the equation that we had before for the momentum equation, we can see that we have the same thing here on the left-hand side as we do on the right-hand side over here. So we can just set this equal to this thing equal to this value right here. Through the use of both the momentum and the shear stress, the energy equations. So we get this equation out of that, and as I just derived, it equals this, and combining them, we get the head loss. This is HL, and we have a new definition now that HF is the term given for the head loss, and that will become apparent in just a minute. But what we're going to do first is we rewrite this thing by multiplying and dividing by basically the kinetic force here, rho v squared over 2, top and bottom, and rearranging things, we get this equation here. So this becomes, this v squared over 2g becomes our familiar head loss kind of term that we used before. It also has two dimensionless numbers, the length divided by the diameter of the pipe, so we can see that the head loss is going to depend on how long the pipe is divided by the diameter. And then we have this term here, 4 tau over rho v squared 2, and this is what is going to be called F. This is the friction factor, and that is why this particular head loss is H sub F. So F is defined, the friction factor. This is a new pi group. It's apparently approximately the shear stress acting at the wall divided by the kinetic pressure. And this is the equation that we get for the head loss in a conduit. We have to determine F, and if we know the length of the pipe divided by the diameter and the velocity in the pipe, we can determine the head loss. Remember that this applies only to fully developed flow, fully developed steady flow, but it can either be laminar or turbulent, and it can also either be round or rectangular conduit. So this is a fairly general equation as long as it's fully developed and steady. That is a key. And so really what we need to do, and what we do in subsequent sections in this chapter, is figure out how to determine F. That's the main thing. So, so that's how we're going to determine the head loss. And one other quick derivation to determine stress distributions in the pipe, just to determine what tau would look like across this pipe, we're going to reapply the momentum equation to this control volume here. We've got just this little cylinder inside here. And just real quickly, again, the momentum flux is going to be 0 because the flow is fully developed, and the momentum accumulation is 0 because the flow is steady. So we're imposing the same restrictions on this, that it's fully developed and steady. So then again, the momentum equation just simplifies to force equilibrium again, and here it is given at the bottom here, and we write down a similar looking equation to what we had before. It's a little bit different. And we can start canceling things out. The main thing is that the pressure times the area both cancel out. So we've got a PA here, pressure area times area minus the pressure times area here, and we're left with dPds minus dPds delta L times A. The other thing to note is that W, as we've seen before in many cases, is actually equal to its gamma times the volume, and in this case that's going to be gamma times A times delta L, and in this case A is going to equal pi r squared. We're going to need that in a minute too. So if we make that connection, plugging in gamma. Oh, and also that the sine of alpha again is equal to dz ds, the change in altitude with the change for a change along the pipe. This being the s direction here, and this being vertical being z. Then that is the sine of alpha. Recognizing that and plugging all these things in, so this is going to become gamma A delta L times dz ds. Now when we divide by this thing, divide by divide through by A delta L, then we're going to get an A here, and we just recognize that that's pi r squared. So that's going to cancel the pi's, and that's going to cancel one of the r's. So we're going to be left with a 2 over r here. I kind of botched that. So it's we can see the 2 over r here. And then really on this side, on the other equations here, we just have a dp. We can reduce this thing to just the change in piezometric pressure, P, plus this is a minus dds of P delta Z. Okay, so again, it's looking like it's actually looking a lot like the Healy-Shaw flow that we saw before. And so when we reduce this equation, moving tau to the other side and basically solving for tau, we're left with r over 2 times this minus dds of the piezometric pressure. And we note a couple of things, and we note that tau is going to be 0 at the center. There's not going to be any shear stress at the center, because when r goes to 0, the shear stress is 0. So at the center of the pipe at r equals 0, that's tau is 0. And then it's going to be a maximum at the edge. And in fact, the shear stress is linear in r. So we're going to get a shape that looks like this. This is what the shear stress inside the pipes are going to look like. 0 at the center and getting increasingly large towards the outside. So that's it. We have an equation here. These are the two major things that we did. We have this equation here that describes the shear stress, and we have another equation that's very important here for the head loss in a pipe. That's going to be dependent upon this friction factor, which we're going to figure out how to calculate it in subsequent sections in this chapter. Okay, thank you.